Hi, my name is Isham, and we are team number 27, and welcome to our final presentation for Chemie 470. In our presentation, we will include the key aspects of providing a profitable and functional styrene production plant. All right, so for the specifications, we met 75% of them, and they were given to us by Knitline Chemicals. We were asked to provide a minimal production rate of styrene, which is equivalent to 98,000 pounds per hour at a purity of 99.8%. We were able to achieve a styrene production of 97,000 pounds per hour at a purity of 99.84%. We were kind of short on the production rate by 1%. However, we met the purity. The reason behind that could be because we had to adjust the flow rates for the streams, as we used a decanter to separate diethylbenzene from water. Another spec we couldn't meet was the recoverable vinyl cyclohexene as a product. The reason behind that is because we did not use a recycle stream for the second reactor.
Hi, my name is Carano. I did a lot of the modeling and process flow technical work for this project. What I'd like to talk to you about today is just a brief outline of our process. We have 1,3-butadiene coming in from a olefins plant mixed with other C4 components. We found it to be easiest to send this through an extractive distillation unit to capture the high purity butadiene as our first reactant. This stream is sent to a recycle, which I'll get to in a minute, where it's combined with a lower composition of butadiene. This feed is fed to a reactor, a packed bed reactor that runs at about 190 degrees Fahrenheit to 210. This produces our vinyl cyclohexene, which is the precursor to the next reaction. This stream comes out and is separated in distillation column 1, where it removes the heavy and light components, which are vinyl cyclohexene and 1,5-cyclooctadiene, and the light components are 1,3-butadiene and 1-butene and N-butane. These streams that are separated, the components that are separated in the light phase, are sent back to the recycle tank, where they're circulated through the reactor again in order to gain as much conversion of the 1,3-butadiene as possible. The bottom of this column is sent to an oxygen mixing station, where it's combined with deionized steam, which is fed from our DI system, oxygen, which is at 50 psi, comes in at about 1.5 to 1 VCHX to oxygen, and the steam comes in at about 2 to 1 steam to VCHX. The other component is the inhibitor that prevents polymerization in the reactor. The second reactor is also a packed bed reactor. This one is a gas phase reaction. It runs at about 700 degrees Fahrenheit, therefore there's a large amount of energy required to get the feed stream up to that temperature, and then again cool it when it comes out. This is done through a complex system of heat exchangers that utilize as much energy in our process as possible without utilizing outside utilities. From here, it's sent into a decanter, which is a 3-phase separator. This takes the organic phase, which is the light phase, the water or aqueous phase, which is the heavy phase, and a small amount of gas phase from the second reaction after it's condensed. And the water phase is collected out of the bottom as a 98% water composition by weight that is sent to a waste treatment facility after being treated for pH by our process. The gas phase that comes out of the top of the decanter is just sent to a flare. We found this was the easiest way to responsibly dispose of this waste stream. And the last phase, or the last stream that comes out of the decanter, is our styrene product that is mixed with other components. In the second distillation column, you can see that there is another distillation column below. The components that are separated in distillation column 2 are the styrene product, and the heavy components, which are mainly benzaldehyde and benzoic acid. These two products are sent to distillation column 5, where they're separated, and the benzoic acid is collected as a product, and the benzaldehyde is not capable of being produced at a high enough purity within our process. Therefore, it is sent to a waste collection tank where we will use it as fuel. The last two distillation columns in our process are primarily responsible for removing all the impurities that are in with the styrene. We do this in a column that is very large and utilizes a very high reflux ratio in order to effectively produce a 99.5% purity styrene out of the bottom of the column. The reason why the reflux ratio is so high is because we're not concerned with the flow rate or any technical details of the distillate, as it's mainly a waste stream and another stream that is sent to a flare. This is done through a partial condenser in order to limit the liquid flow rate in the column from being astronomical. The last column, it takes the styrene product out as a distillate, which is a relatively unusual approach, as it's a heavier component. However, it's being separated from residual heavy components such as benzaldehyde, benzoic acid, the cyclooctadiene from the first reaction that may have traveled through the entire process up to this point. And the distillate is collected as 99.84% by weight styrene. And before this stream is sent to the product storage tank, it is cooled through a series of heat exchangers that utilize, again, energy in our process. And before it is sent to the product storage tank, it's refrigerated. It's required to be at 50 degrees Fahrenheit and atmospheric pressure to prevent any sort of polymerization or other catastrophic phenomenon. That is our process in a nutshell. Thank you very much.
All right. The first byproduct I'd like to talk about is the benzoic acid that exited from the bottoms of distillation column 5. We were able to sell this for 1.27 cents per pound. The distillate was made up of benzaldehyde, and that exited through the waste streams. The second byproduct I'd like to talk about are the waste credits. Now, this is a combination of all the waste streams in the process, and this was able to sell for 5.7 cents per pound. Now, if you look at the pie chart, you will see that the waste credit makes up the majority of the revenue obtained, and that is largely due to the fact that the flow rate of the waste credit is much higher than that of the benzoic acid. The total revenue generated by the byproducts is 6.98, a little under 7 cents per pound.
My name is Nick Caravan, and I worked on the economic analysis for our plant. And here are the raw materials, and they dominated the operating costs. The pie chart explains it pretty well. It's laid out here well. The raw materials was over 57.6% of the total cost. The raw materials contained 4-tert butyl catechol, high pressured oxygen, and the feed gas, which was C4s, mainly 1,3-butadiene. The feed gas was over 80% of the raw materials, and then the high pressured oxygen and 4-tert butyl catechol was the rest of the 20%. The next part we had was waste costs, 17.6%. This was the wastewater. This was due to the very high flow rate of it and also the cost. The next part was utilities, 14.8%. This dealt with high pressure stream, low pressure stream, medium pressure stream, cooling water, electricity for the pumps, and this also dealt with heat exchangers, distillation columns, everything else. Now, to get to some smaller costs, we had the selling, guide, and administrative costs, which was 1% of our cash flow. That maintained 8.4%. And then we had some smaller costs, such as labors. We had 8 operators working at $85,000 a year. And then we also had taxes on that. So these were the main costs for operation. The total capital cost for the OBL was $80 million, and this incorporated the raw materials storage, the utilities, which I had discussed, the environmental part of it as well, and this created the total capital cost to be over $200 million. Now, the next part we had was the current point estimate, which include team costs, miscellaneous costs, and other things, which were a percent of the total capital costs. And this percent was multiplied by the total capital cost and added on to it. Now, the one fixed cost we had, in addition to these, were the catalysts. for both reactors, the monocyclohexane reactor and oxidehydrogenation reactor. Now these costs were fixed, as I mentioned, and had to be renewed every 3 years. The plant life cycle is for 15 years, so these were multiplied by 5. The last part we had was the total plant cost, and all the costs so far. There was an inflation 3% for 3 years, and a contingency plan of 25%. So we had to multiply what we had so far, what costs we had, by 0.34, and add that to the total cost, which gave the total plant cost to be over $360 million. Product price changes with the market. So we were given a cost of 65 cents per pound in the background for this project. Now, as you can see on the right, there's a chart for U.S. styrene prices. On the x-axis, it was for time, and it was over a 3-year period from April 2015 to April 2017. On the y-axis, it was dollars per metric ton. Now, after multiple calculations, we found out that the average price for styrene per metric ton was around $1,066.67. This converted was $44,555 per hour. Now our cost was around $60,851, which about a $15,000 increase could create some problems, which we will get to next. Now I'm going to talk about the cumulative cash flow model, and here are just some of the specs we had to insert into the cash flow model right behind me. I've talked about a few of these already, the SG&A and inflation. The working capital was 10%. The discount rate we had, which affected the net present value, was 12%, and the income tax rate was 34%. Now we are starting this plant in January 2021, the expected plant life cycle of 15 years. So from 2021 to 2024, we are going to be designing and constructing the plant for construction. At 20%, 30%, and 50% will be the augmented reality spend. And for the capacity and sales build, they'll be at 33%, 65%, and 90% for the first 3 years. Now the main two figures I want you guys to look at are the plant capacity and plant capital. The plant capital for styrene was calculated at 808 million pounds per year. And the plant capital, which involved the total capital costs of the OBL and IBL as mentioned before added together, plus the $135.5 million capital cost for the 1,3-butadiene extractive distillation column. And these affected our cash flow model to get us a negative value, which I will talk about in the next slide. So the current net present value dissuaded us from production. So after the analysis, we found out that the net present value of our plant at 2036 would be around negative $151 million. The IRR, the internal rate of return, could not even be calculated because the ATRR, or after tax rate of return, was a negative number. So this was not able to be calculated. The required netback to meet the minimum values we needed of $30 million for net present value and 20% of after tax rate of return was over $230 million, which was a 56.6% increase from the average cost. This is a very steep increase, but if you go back to this slide, the highest cost right there was around $1,400 per metric ton, and we would need it to get to about $1,600 per metric ton. So it's not impossible, but it's very unlikely that we would be able to compete with other styrene plants in the United States.
Hi, my name is Brian Weisner, and I am a part of Group 27 for the production of styrene. In our process, as many of us have mentioned, we actually were unable to make money, and I would like to talk to you about some of the specifications that would need to change for this to be able to be a profitable course of action. So the main one is actually the styrene price. As many of my group members have mentioned, the styrene price is actually fluctuating throughout the years. To make profit for our plant, we would actually need about a 57% increase in styrene price. So this is going from as we can see, 65 cents per pound of styrene to 74 cents per pound of styrene. This isn't the only thing that we can do to change our process, however. There's a few other courses of action that would allow us to yield improvement in our process. One of them, as I've previously stated, is money. And then the next one would be a change in our process. So extractive distillation costs $130 million a year, plus licensing for our utilities. If someone were to take up this project, it would be very plausible that they could come up with a multiple stage distillation separation, or even use other separation units to garner the same amount of separation and purity out of the product stream and be able to do this with much less capital, and thus increasing the profit that you can make throughout our process. And lastly, as I've almost already touched on, is we could actually change the amount and usage of certain separation techniques. So in our process currently, we are using a lot of distillation columns, and we are using one decanter. A very good example of this is in industry. A lot of processes use membranes as part of their separation techniques in order to purify the styrene to a limit where it is saleable with very little effort and very little cost. So since we were barred from these methods, we were unable to explore these. However, they are definitely an option for future recommendations. So on part of Group 27, we would all like to thank you for watching our presentation, and have a nice day.
All right, that's good enough.